collection of atoms sitting there. How can it possibly behave like a gas of particles? It sounds completely counterintuitive, right?
Really does.
But what if I told you that deep down, even the most ordinary materials have this hidden quantum life, a really vibrant, dynamic thing going on made of tiny waves and particles?
That's exactly what we're diving into.
Today, we're taking a deep dive into the world of phonons. These are the quanta of vibration in a solid, and we'll explore their surprising, really fundamental connection to something called the de Broglie wavelength.
Yeah, our mission here is to unpack how these, well, classical ideas about atoms just jiggling around in a solid lattice actually merge pretty seamlessly with quantum mechanics.
And this merger gives birth to something new.
Exactly. It gives birth to this particle-like entity, the phonon. And understanding phonons explains so much from how heat moves through your coffee cup, basic stuff, right up to how scientists probe materials with really advanced techniques.
So it's a journey from the everyday macroscopic world down to the quantum level.
Precisely. And it reveals this really profound unity.
Okay, so let's set the stage. We have to start, I think, with one of the biggest ideas from the early 20th century. The total breakdown of that old distinction between waves and particles. Before then, things were one or the other. Light was a wave, an electron was a particle. Simple.
But not correct.
Right. Everything changed.
That's right. After Einstein showed that light waves could act like discrete packets, photons, we call them now, Louis de Broglie had this incredible insight in 1924. He thought, well, maybe there's a symmetry here.
If waves can act like particles,
then particles must act like waves. It's the core of the de Broglie hypothesis. Anything with momentum, Pili, has a wavelength lambda. And the genius was linking it through momentum. That gives us lambda equals h over p, Planck's constant over momentum.
And this wasn't just theoretical musing. It got confirmed really fast.
Amazingly fast.
Yeah.
1927, Davisson and Germer, they shot electrons at a nickel crystal.
And saw diffraction, the classic sign of a wave.
Exactly. The wavelength matched de Broglie's prediction perfectly. And since then, we've seen this duality for neutrons, atoms, even huge molecules like buckyballs. It's universal.
Fundamental.
And in modern physics, we often use slightly different terms like h-bar, the reduced Planck constant, and k, the wave vector, and omega, the angular frequency. It gives us p equals h bar k and e equals h bar omega.
A more elegant formulation.
You could say that.
Yeah.
It gives this unified picture where something behaves as a wave or a particle depending on how you measure it. It's really a cornerstone of quantum mechanics.
Okay, so that's wave-particle duality for fundamental bits like electrons. But how does this very quantum idea apply to something solid, something macroscopic, like, I don't know, a block of metal? Let's pivot to the crystalline solid itself.
Right.
It's not just a random jumble of atoms, it's ordered, repeating, a lattice structure.
And in the classical picture, these atoms aren't static. They're constantly jiggling, oscillating around their average position.
It's like they're connected by springs.
That's a great analogy. We model the forces between them, like elastic springs. It's called the harmonic approximation. It lets us treat the whole crystal, trillions of atoms, as this huge network of coupled oscillators.
Okay, let's unpack that. If one atom jiggles, because they're all connected.
It affects its neighbors. That motion propagates through the whole lattice.
Ripples?
Exactly like ripples. These are collective vibrational waves, or lattice waves, traveling through the solid.
And here's the potential disconnect, maybe. De Broglie waves for single particles versus these classical collective waves in a big object.
That's the gap we need to bridge. How do these two seemingly different ideas actually connect? That's what we're getting into.
So how do we bridge it? We have all this chaotic thermal jiggling.
Right. But mathematically, we can decompose that chaos into something orderly, normal modes.
Normal modes, like on a guitar string.
Precisely like a guitar string. Each specific vibration pattern, the fundamental of the harmonics, is a normal mode. In a crystal, each normal mode is a collective wave where all atoms oscillate at the same frequency, omega. And it has a specific wave vector, k.
And that wave vector k, that defines the physical wavelength of the distortion.
Yes. Lambda lattice, we call it. It's just 2 divided by k. It's the literal distance over which the pattern of atomic displacements repeats in space.
The length of that wave of jiggles.
Exactly. And the way the frequency, omega, changes with the wave vector, a, that's the phonon dispersion relation, feet. It's a unique fingerprint for every material.
Determined by the crystal structure and the forces? The springs.
Correct. It tells you everything about the lattice's dynamics.
So we have these classical waves. Now, bring in quantum mechanics, what happens to the energy of these waves? Can it be anything?
No. And here's where it gets really cool. Classical physics says continuous energy is fine. But quantum mechanics insists that the energy of any harmonic oscillator, including these lattice vibrations, has to be quantized.
Meaning discrete steps, not a smooth ramp.
Exactly, a staircase. Energy only comes in specific packets.
Yeah.
And that quantum, that packet of vibrational energy, that is the phonon.
Introduced by Tam, named by Frankel, analogous to the photon for light.
A perfect analogy. A photon is a packet of light energy. A phonon is a packet of vibrational energy. Its energy is essentially h bar times omega. And the total energy in a mode is quantized. You can have 0, 1, 2, 3 phonons, but never 1.5.
So this brings us to the idea of the quasi-particle. Explain that.
Right. A phonon isn't a fundamental particle like an electron. You can't, isolate one outside the crystal. It's an emergent thing.
Emergent.
It arises from the collective behavior of the whole system. It behaves like a particle, even though it's really a pattern of motion of many atoms. Think of a wave in a crowd at a stadium. It moves like a thing, but it's just people standing up and sitting down.
That's a good way to put it. And this concept is useful.
Immensely useful. Instead of tracking trillions of atoms, which is impossible, physicists can treat the thermal energy in a solid as a gas of these phonons moving around.
A phonon gas.
Yeah. It simplifies the problem massively. It's how we understand heat capacity, thermal conductivity. Especially in insulators, heat flow becomes like the movement of this gas of quasiparticles.
Now, you mentioned crystals can have more than one atom per unit cell. That complicates things.
It makes things richer. The dispersion relation splits into branches, generally 2 main types.
Okay.
First, acoustic phonons. Atoms move mostly in phase, like sound waves. For long wavelengths, their frequency is proportional to k, and the slope gives you the speed of sound. Hence, acoustic.
Makes sense. And the other type?
Optical phonons. Here, atoms move out of phase against each other. Even at k0, they have energy. If the atoms are charged ions, this motion creates an oscillating dipole.
Which can interact with light, optical phonons.
Got it. And another key idea is the Brillouin zone. Because the crystal repeats in space, its properties repeat in k space too.
So you don't need infinite k values.
Exactly. All the unique vibrations can be described within a finite region around k del Nero, the first Brillouin zone. It also means there's a minimum wavelength possible related to the atom spacing. About twice the lattice spacing, roughly. You can't have a wave shorter than the atoms themselves, essentially.
And this whole framework, normal modes, quantization, phonons, branches, Brillouin zones, this connects the microscopic quantum world to things we can actually measure, like heat capacity.
Absolutely. Models like Debbie and Einstein use this phonon gas concept to explain macroscopic thermal properties. It's a really powerful bridge.
Okay, but let's tackle that momentum question again. If a phonon is particle-like, does it have real momentum? Like, if you create a phonon, does the crystal recoil?
Great question. And the answer involves making a careful distinction. There's physical momentum, the sum of mass, times velocity for all atoms. It's tied to the center of mass motion.
Right.
For a phonon, atoms oscillate, but there's no net movement of mass across the crystal. So a single phonon carries 0 net physical momentum. The crystal doesn't recoil.
But it seems like it should have momentum in some sense, right? It interacts, it scatters.
It does, but it's a different kind of momentum. We call it crystal momentum or quasi-momentum, defined as h bar times k.
Why crystal momentum?
Because it arises from the symmetry of the crystal lattice, its repeating nature. Physical momentum comes from the symmetry of empty space. Crystal momentum is conserved in interactions within the crystal.
So it's the quantity that matters for scattering inside the material.
Precisely. It dictates the rules what scattering events are allowed. But its conservation law has a twist.
A twist.
It's conserved modulo h bar g, where g is a reciprocal lattice vector. Basically, the crystal lattice itself can soak up or provide discrete chunks of momentum without really changing.
So that's why K is confined to the Brillouin zone. Anything outside is equivalent to something inside plus one of these chunks.
You've got it. So while it's not true physical momentum for all practical purposes inside the crystal, h bar k is the phonon's momentum that governs interactions.
Though you mentioned the line can blur sometimes.
In certain situations, yes. Finite size, temperature gradients, subtle effects can give phonons a tiny bit of physical momentum. It's related to things like radiation pressure from heat flow. But mostly, we focus on crystal momentum.
Okay, now let's bring it all home. The core synthesis. We have de Broglie's universal relation, lambda equals h over p. We have the phonon with its crystal momentum, h bar k. How do we connect them?
This is the beautiful part. We take the de Broglie relation.
Yeah.
Lambda equals h p.
Okay.
We substitute the phonon's relevant momentum, its crystal momentum.
Right.
P h h r k.
Right.
Now remember, h bar is just h divided by 2, so lambda exact h2 jk.
The h cancels.
Exactly. And you're left with lambda Broglie's 2k.
Wait a minute, 2k. And that's exactly how we define the wavelength of the classical lattice wave earlier. Lambda lattice.
Precisely, so the fundamental identity drops out.
And
Lambda Broglie is identically equal to lambda lattice.
wow, okay. That's neat. But what does it mean? Why is that identity so important?
It's more than neat. It's profound. First, it's stunning confirmation that wave-particle duality holds even for these collective things, these quasi-particles.
The phonon is both a particle-like quantum and a wave-like distortion.
Yes. And the waveness described by de Broglie is the physical waveness of the atoms jiggling. It's perfect self-consistency.
Okay, what else?
Second, it validates that whole phonon gas model. If phonons have a well-defined momentum and a corresponding de Broglie wavelength, treating them as particles in a gas makes sense. That's crucial for understanding thermal properties quantitatively. Their wavelength matters for things like heat conduction.
And third, you mentioned experiments.
Yes. This identity is the absolute bedrock of phonon spectroscopy. When you scatter something, say a neutron, off a crystal, it exchanges energy and momentum with the phonons. By measuring the neutron's change in momentum, delta p, the identity tells us lambda equals h delta p. This means we are directly measuring the wavelength of the lattice distortion the neutron interacts with. It connects the quantum scattering event to the physical wave in the crystal.
It's how we can see these phonons.
Exactly.
So how do we see them? What are the main techniques? You mentioned neutrons.
Right. The gold standard for mapping out the entire phonon dispersion relation is inelastic neutron scattering, INS.
Why neutrons?
They're perfect for the job. Their energy is naturally in the range of phonon energies, milli-electron volts. And crucially, their de Broglie wavelengths are around angstroms, the same scale as the spacing between atoms.
So they can see the lattice structure and the vibrations?
Perfectly. They diffract off the atoms, and by measuring how much energy and momentum the neutron loses or gains.
You know the energy and momentum of the phonon it interacted with?
Precisely. You can map out the whole curve across the entire Brillouin zone.
And neutrons talk to everything.
Pretty much. They interact with the atomic nuclei, so there are very few selection rules. They see almost all the vibrational modes. It's very unbiased.
Okay, what about other methods, using light?
Yes. Raman and Brillouin spectroscopy are complementary light scattering techniques. Raman usually looks at higher energy optical phonons, Brillouin at lower energy acoustic ones.
Different mechanism though, right? Light interacts with electrons.
Correct. Photons interact with the electron cloud, not the nuclei directly. This means there are stricter selection rules based on symmetry. A phonon has to change the material's polarizability, how easily its electron cloud is distorted by light to be seen.
And there's that momentum issue.
Yes, the big one. Visible light photons have tiny momentum, tiny k, compared to the size of the Brillouin zone. So by momentum conservation, basic light scattering can really only see phonons very close to the center of the zone, where k is near 0. We call it the QO0 selection rule.
So light scattering normally misses most of the picture.
For simple first-order scattering, yes. But scientists are clever. They use tricks. Like in nanocrystals, the small size relaxes the rules. Or they engineer superlattices. And there are complex, multi-step scattering processes like in graphene's Raman spectrum that can actually probe phonons across the whole zone.
So summing up the techniques.
INS gives you the full picture, the whole dispersion that needs big facilities, like a reactor. Light scattering is easier, benchtop setups, great energy resolution, but usually limited to near k=0 and has more rules. They really work together.
Okay, so wrapping this all up, this connection, the phonon's de Broglie wavelength matching its physical lattice wavelength, it's clearly fundamental.
It's a cornerstone of solid-state physics. It answers that initial riddle, how a solid acts like a gas. The particles in that gas are the phonons.
In this success story, using phonons, it set a pattern.
Absolutely. It established the whole quasi-particle paradigm in condensed matter physics. Find a complex collective behavior, simplify it by treating it as a gas of emergent particles.
Like phonons, what are some others?
Oh, there's a whole zoo. Electron quasi-particles and holes in semiconductors, magyons for spin waves in magnets, plasmons for electron gas oscillations in metals, polaritons, which are hybrids of light and matter.
So the strategy is always to find the right quasi-particle to simplify the complex reality.
Exactly. It turns intractable problems of trillions of interacting things into manageable problems of weakly interacting quasi-particles. It's how we make sense of the quantum world inside materials.
It's quite an elegant approach.
It really is. The journey from just atoms jiggling classically to the quantum phonon and seeing how perfectly its de Broglie nature matches its physical wave nature. It's a beautiful unification within the solid state. It shows that even a collective buzz of the whole crystal behaves like a proper quantum entity.
So the next time you feel the ground under your feet, solid and stable,
Or feel warmth radiating off something.
remember you're actually experiencing this incredible hidden quantum dance. Countless particle-like waves constantly moving, interacting, carrying energy.
It's the hidden reality, the unity and complexity just beneath the surface of everything solid.